Okay, so now we're on rigid body statics. We started talking about that, back to rigid body statics. We talked about how to calculate moments, and we talked about these special kinds of moments that are produced by couples. The definition of a couple is really two equal and opposite forces, but we're going to think of them as just adding a moment onto things. And the reason we're going to think about them that way is they don't produce a force because they're equal and opposite, so they add up to zero force. And they produce the same moment no matter where your about point is. Okay, that was the derivation that I did. And so now we're going to start using these in statics problems. So I'm going to start out with this. So let's say we have this body, a disk, and let's say that there's an unknown force over here, an unknown force vector. I'll call this force vector F1, 2, 6. And then over on the other side, let's say there's a force with a known direction. It has a magnitude F2, and it makes an angle of 30 degrees with the horizontal. And then down here at the bottom, there's a couple applied. Now that couple really is two equal and opposite forces, but I'm just going to represent it as a pure moment of 450 Newton meters. Right. And I could have, an equivalent way to write this would have been to have it look like it's going the other way. And, oh, actually, let's make this a negative. Yeah, I could have made it go the other way with a negative on it. But this symbol, people use this a lot for two-dimensional statics and two-dimensional models. That's sort of misleading about what this is, remember. Remember that a moment is always a vector, okay? And so to think about the direction of that vector, you have to use the right-hand rule with that rotation. Okay, so if it's going this way, that's a moment in the positive z direction coming out of the board. Okay, this one, and then with the negative, that makes it flip the other direction. And let's, so the counterclockwise is positive, and then the negative on the number says, you know, that it actually goes the other way. So that says that as a moment vector, that is 0, 0, negative 450. Which, on which? On the couple? Yeah. The moments you have a counterclockwise arrow. Right. That indicates positive. Yeah, so that's the same as like if I had written this with a negative, you know, I said it was going this direction and this was negative F2, that would be the same thing as F2 going this direction. Because if you multiply any vector by -1, it switches the direction. Okay, think of that as like something you're multiplying to a unit vector. Okay, so let's calculate what are F1 and F2 if this object is in equilibrium? And I'm going to do this calculation. When you do this, you can choose any about point you want for moments. I'm going to choose my about point here. Okay, that's going to be my A. So I'm going to set up this table with rho, force, moment. And we need a radius for this. Let's say that the radius of this disk is 0.5 meters. Okay, so I'm going to start with the force F1. The rho vector goes from the about point to where the force is applied. Okay, so we need to figure out a vector that goes from A to where F1 is applied. Okay, so how do you get from A to F1? You go 0.5 meters down and then 0.5 meters over, right? That's your negative y direction and negative x direction. So that rho vector, if I do it in 3D, is negative 0.5, negative 0.5, 0. With me on that? And then the force vector is F1x, F1y, 0. And so the moment produced about A is negative 0.5 F1y plus 0.5 F1x. Yes?
Do you typically not write the moment as a vector?
That is a good, I do want to right now. Thank you for. So pretty soon I'll start writing it as a scalar just to save time and whatever. But yes, I did want to do that. So it's 0, 0, and then the z component is negative 0.5 F1y plus 0.5 F1x. Okay, that's what it is as a vector. Any other questions? Okay, now let's go to the other force. So what's the rho vector for this force F2? So we want the vector that goes from A to where F2 is applied. Yeah, so positive 0.5 for X, negative 0.5 for Y, and then 0 for Z. The force vector yeah, exactly. So if this is the coordinate system, and that's the vector, it has a magnitude of F2, and we know that this is 30 degrees. So from the positive x-axis, that's 180 minus 30, so 150. And so this force vector is negative 0.866 F2, positive 0.5 F2, and and then 0 for z. Then take the cross product of those two, and the moment is 0, 0. And then for z, it's 0.25 F2 minus 0.433 F2 and so that is 0.183 negative. Is that right? F2. Okay, and now we get to the couple. And for the couple, we don't care about these. It's not going to produce a force. And we don't care about its relationship to any about point because it produces the same moment around any about point. All we care about is the couple, and the answer there is 0, 0, negative 450.
So that's for the couple there?
Yes.
And the second part was for force two?
For
The second variable,
this stuff?
yeah.
Yeah, we don't care about the row vector because.
Right, that's for the moment.
Yep, and then for force, we don't care about that because a couple is always equal and opposite forces, so they add up to 0.
The second row, that's for friction.
Oh, yes. Oh, I see what you're saying. Yes, that's F2. Yep. Yeah, that's F2, and this is the couple, the 450. And now we can go to Newton's second law. How many Newton's law equations are we going to get here? 3. It's a two-dimensional problem, so we're going to have 2 useful equations for Newton's second law plus 1 useful equation for the moment equation. Okay, so Newton's second law first. Okay, so do we expect to be able to solve this? Yeah, because how many variables do you have? 1, 2, 3. So 3 equations, 3 variables. As long as nothing funky happens with linear multiples, we should be able to solve this. Okay, so Newton's second law, what we're going to do, this is what's nice about this table. We're going to take all these and just add them all up, and that's the left side of Newton's second law. So we have F1x, F1y, and I'm going to leave off the z's because the z's are always going to be 0 for a two-dimensional problem. And then plus negative 0.866 F2, positive 0.5 F2, and that's everything. So since it's an equilibrium, those add up to 0. And then for the moment equation, rotational Newton's second law, I'm going to take all these and add them together, and that gives me the left side of the rotational equation. If we did it for x and y, for each one, we just get 0 equals 0. You know, that doesn't help us at all. So I'm just going to write down the z equation. So we have negative 0.5 F1, F1y plus 0.5 F1x minus 0.183 F2 minus 450 is equal to 0. You could solve this by substitution, but I'm going to write out an augmented matrix and we'll do it that way. So we have 3 equations. That means 3 rows, 4 columns. And the order I'll go in is F1x, F1y, F2, and then the constant. And these are equations 1, 2, and 3. The first equation is the x component equation for Newton's second law. So F1x's, we have 1. F2's, we have negative 0.866. And the other 2 are zeros. The second equation is the y equation from Newton's second law. We have F1y, we have 1 of those. F2, we have 0.5. And then zeros. And then the third one, F1x's, we have 0.5. F1y's, we have negative 0.5. F2's, we have negative 0.183. And you have to move the constants to the other side, so the constant is positive 450. And if you do reduced row echelon form, you get the same size matrix back. Where these are 1s and 0s like this. And the answers are going to be given in the order F1x, F1y, and F2. Anyone happen to be punching this in? 779.4, okay. Okay, great. So with forces, loads applied in this pattern, for that thing to be in equilibrium, you know that the values have to be what we were given below. So that's a statics problem. And that's, you know, basically what we're just going to keep doing from now on. There's one more thing that, so say this disk represents something that you see out in a playground or whatever, and you want to calculate these loads. There's one more step that we need to take to go from what you see out in the world to doing these calculations. And that's figuring out what the forms are for the type of loads that you, like this thing might be, like here, it might be attached to the cement or something, okay? And here, it might have a hinge joint or something. And here, a pole might be pushing on it or whatever. So how do you go from the way that it's attached to its surroundings to figuring out how to represent those attachments as loads? Okay, That's going to be a really key thing in this class. And so that's the topic of joints. How do you represent different kind of joints? And that's what we're going to get into now. We're going to start with joints in 2D. And pretty soon we'll get into joints in 3D, how to treat them in three-dimensional problems. But think of joints as just connections between bodies. And the way you need to think of joints is the key thing that they do is they limit the motions of bodies. And in what ways they limit those motions is going to be the way to understand what kind of loads they apply. Okay, so the key thing is always going to be like the presence of this joint, how does it limit the motion of this object? So in order to understand this, so first, imagine an object floating in deep outer space. And this is a 2D object. I'm just thinking about the motion in 2 dimensions. Well, it's capable to produce 3 different types of motions to this object. And these 3 types of motions are called the degrees of freedom. 3 motions possible. So the degrees of freedom. It's capable of, so this body, so somehow you're out there in deep outer space, alive still, and capable of moving this object around, okay, this 2-dimensional object. So first you can move it, you can translate it, this thing's hovering there, and you can choose any axis you want. You can translate it along that axis, okay? Okay. Second, you can translate it along an axis perpendicular to the first one. So along an axis perpendicular to the first axis. And with those 2, I mean, you're used to this idea for coordinate systems, but with those 2, you can translate it anywhere, no matter what your choice of the first axis was. If it's over here, you can move along this axis until here, and then down that way, you know, you can get anywhere you want. And then the third one is this thing's orientation can change, right? So this one is a rotation in the plane. Okay, so in other words, rigid bodies in 2D have a maximum of 3 degrees of freedom. Two are translational and one is rotational.
Are we talking two-dimensional space or a two-dimensional object?
Two-dimensional space. 2 translational and 1 rotational. Okay, so now think of what would be required to take away these degrees of freedom. So what would be required to take away each of these degrees of freedom? Okay, so first, now this is the object's ability to translate along that first axis. Okay, so say you tried to translate this object along this axis and it wouldn't move. Okay, that means that something else is applying a force along that axis that counteracts whatever you're doing to it. Okay, so there's a force. Each of these degrees of freedom question mark. So if the right force was applied along the axis, that would take away the object's ability to be translated along that axis. What about the second one that's perpendicular to that? Well, same thing. So that would have to be a force perpendicular to the first axis. And then what if, say, it could translate anywhere, but whenever you tried to change its orientation, it wouldn't go? What would it take to take away that degree of freedom? That would require a couple. And so by thinking about what degrees of freedom a joint takes away, you can figure out what loads are applied by that joint. So for example, of all the types of joints we're going to talk about, the last one we're going to talk about is a fixed joint, or sometimes it's called a weld joint, but it just says the two objects are rigidly connected. Okay. And so with all of these, what you want to do is think about nothing acting on the object except that joint, and then think about how many degrees of freedom have been taken away from the 3 this thing would start with in outer space. Okay. So if you had an object and you welded it to the table, would you be you able to translate it? Would you be able to translate it perpendicularly to that? Would you be able to change its orientation? And so all 3 degrees of freedom are taken away by a weld joint. And that means that the weld joint applies a force along some axis, a force perpendicular to that axis, and a couple. Okay, so that's the thought process that's going to let us go from looking at a thing in the park, and like you see a hinge here and this here and you know, to saying, in the free body diagram saying, I know there's a force in that direction. Over here, I know there's a couple, and so on. Okay. So now I'm just going to go through a list of all the 2-dimensional joints that we're going to see in this class, and I have 2 examples that hopefully will kind of help understand. And I'm going to go through it in terms of categories. Each one of these categories limits certain types of motion. Okay. So joint category 1. These are the joints that apply a force in one known direction and how many variables does it take to represent a force with an unknown magnitude but a known direction? 1, that's right. So because you have the magnitude that's a variable, f or something, and you're multiplying it by a unit vector that you know, okay? Therefore, these introduce 1 variable into Newton's laws. Okay, the first one of these is contact without friction. We've already dealt with this one. So this would show up in a problem like this. There's a surface, and then there's a body that makes contact with it like that. Let's say this is body 1 and this is part of body 2. Okay. So a free body diagram of body 1. Would have a force perpendicular to that surface. I'll call that R. And if you were doing a free body diagram of body 2, so it's just like a chunk of the ground there, it would be equal and opposite. Same magnitude, but opposite direction. Okay, so let's think about this in terms of those degrees of freedom. Okay. So first, can you find an axis where this thing is not allowed to move? Yeah, it can't go this way along the axis, right? The ground stops that, okay? So we know there's a force perpendicular to and that's what we see here. There is one thing, this could jump up off the surface. So if you ever do a calculation like this, assume the force is that way, and you get a value for R that's negative, that says that that force in your calculation is pulling down on that object, like it's glued, and in most applications that means either you mess something up with your calculation, or this idea that you have isn't going to work. Okay, that needs to be a positive answer because it needs to be a pushing contact. It can't be a pulling contact. Okay, so we decided that there's a force perpendicular because it limits that degree of freedom. Okay, what about the axis perpendicular to that? Can it move along that axis? Yeah, so there's no force perpendicular, and there isn't one in that free body diagram. And what about changes of orientation? Can you rotate this thing? Yeah, and so there's no couple. Okay. So one thing to notice about this, I mentioned this a second ago, but that R value has to be positive. The second joint in this category is a roller. There are really two ways that you see this drawn. One is, so I'll say this body is like that. We'll call this body 1. And this is body 2. Or the other way you see it drawn is like this body is wearing a roller skate. In this case, a free body diagram of body 1. Again, this is a pushing force perpendicular to the surface of contact, so is like that. And then a free body diagram of the second body would be equal and opposite. And again, think about what degrees of freedom are removed by this joint. And when you're thinking about these joints removing degrees of freedom, imagine that the joint is connecting it to something rigid, to the ground or something. Okay, so don't think of this as another body that's able to move, even if it is. Okay, you have to think about it as if that's fixed. Now, what does the joint with that fixed body do to limit the motion of the one? So body 1 here, can you find an axis where translation is removed? Yeah, it can't translate up or down. Okay, and so there's a force there. Now the axis perpendicular to that, is translation removed? No, it can roll. So there's no force perpendicular to that. And what about rotations? Can it do this? Yeah, it can do that, so there's no couple. Would be what? It would, yeah.
Okay.
That's right. So in 2 dimensions, couples, any kind of rotational thing can only be about the z-axis. Z or negative z, yep. What do you think about the sign of this r? Can it be either, or does it have to be positive? Yeah, has to be positive because this can only push. So notice r has to be positive. And then the last of this type of joint is a pin and slot joint. Yep, these are all in the first category because they all introduce one direction force, a force with a known direction, and they all introduce then one variable into the equations. So a pin and slot is like these are the 2 bodies, and that pin that shows up in that first one can slide up and down that slot. So this is body 1, this is body 2. And I have one of these, one of its little, one half of the pin broke off. But okay, so what this thing can do is, it can do any of that. Right, so yeah, let's just go in order, but yeah, it's free to rotate, and so we're gonna imagine that the fatter part is fixed and see what this joint lets this thing do. So can you find an axis that restricts translation of this object? Yeah, if I try to push it or pull it perpendicular to that slot, it won't go. Okay? So it has to apply a force perpendicular to that slot. What about perpendicular to that first axis? So along the slot. It can translate. And so there's no force there. Rotations? No, it can rotate. So there's no couple. So the only force is perpendicular to that slot. Okay? That's the only load that's applied. Yeah. Mm-hmm. Okay, so what you're always asking yourself is there any axis, try any direction, where you try to translate this thing and you're stopped? Just moving up and down without changing orientation.
What plane is that in?
You're looking at the plane. Okay, so like, do you see how this, like, look at it compared to this picture? It's like that. See what I'm talking about? Okay, so is there any axis where if I try to move it along the axis, I can't do it? And the answer is yes. If I go perpendicular to that slot, if I try to go this way, it runs into one side. If I try to go this way, it runs into the other side. Okay. And so a free body diagram of body 1 is perpendicular to that slot. If that slot, so Like if this is the direction of that slot. Then these are at 90 degrees. But if I try to translate it along the slot, it translates freely. If I try to rotate it, it rotates freely. So that's all there is. Again, I'll call this R. And then if I drew a free body diagram of the second body, it would be, that force would be the same direction, or parallel to it, but opposite direction. God damn it. This is so annoying. Okay, R. Okay, those two are equal and opposite to each other. What if I did this calculation and thought that R was negative? Is that possible in this case? Yeah, but because of the way this joint works, it can push. If I try to push it down, it stops me. And if I try to pull it up, it stops me. So this one, unlike the other two, can work in both directions. So notice that with this one, R can be positive or negative. Mm-hmm. Any other questions about, so that's all the three types of joints in this first category that introduce one variable. This is a 2D problem, so when I say that these introduce one variable, how many total variables, how many total unknown, variables can you solve for with Newton's laws? 3, yep. You have 3 equations, the x and y equations for Newton's second law, and the z equation for the rotational. Okay, so if you have one of these 3 types of joints, you can solve for 2 other variables along with it. Okay, so now we're going on to joint category 2. And there are 2 in this category, and each one applies a force with an unknown direction. So you can think of that as 2 force components, 2 unknown force components. And so how many variables are introduced into Newton's laws if you have 2 unknown force components? It introduces 2 variables. Okay, so if you had a rigid body that had one of the first category joints and one of these second category joints that I'm about to talk about, you could do the calculation because that would be, 3 total variables, you have 3 total equations, and you can work with that. But if you had 2 different joints in this second category, there's no way using statics to do that calculation. It's not about like whether you're clever enough. There's no way using statics that you can use 3 equations to solve for 4 variables. Okay, so when you look at problems, a lot of times, at least simple problems, you can kind of count up like, okay, I know this is how many variables are going to get introduced. Here's how many equations I'm going to have. This is going to work or this isn't going to work. Okay, so the first one of these is a pin joint, or you can think of that as a hinge. And this looks something like this. Where this is body 1 and this is body 2. Even in pretty advanced studies of like biomechanics, this is mathematically how people tend to treat knees and elbows, you know. And I have a pin joint here. Okay, so it can, well, there's a lot of friction, but imagine there's no friction there. Can you find any axis where, so say this is the object, the top one here is the object that we're analyzing, and I'm imagining this other one is fixed. Can you find any axis where I'm prevented from translating this top body? Yeah, any axis you choose, you can't translate it, right? If I try to go this way, or there's no direction that you can translate it. So that means that choose your first axis, there's a force in that direction. Choose an axis perpendicular to that, there's a force in that direction. Okay, so you can think of that as an unknown force vector. There's a full vector of unknown forces that limits that motion. What about rotations now? Yeah, I can rotate it freely. And so there's going to be an unknown force vector, but no couple. So a free body diagram of body 1. We'll just represent like this. I'll call that F. And actually, let's do this with the subscripts. So we have this vector F. The way the subscript notation for forces works, the first subscript is the body that's being acted on, and the second subscript is the one acting on it. So this is the force acting on 1 by 2. So think on 1 by 2 or on A by B. Okay, that's what those subscripts mean. And then the second body that's equal and opposite. We can write that as, so this force vector is the force on 2 by 1. And Newton's third law says that that is negative F1, 2. Okay? Any questions about that? What about the signs of these? So imagine body 2 being fixed to the ground. Could you have positive components? Yeah, could you have negative components? Yeah, I mean, it's all just like, yeah, no matter which direction you try to move, that force will keep you from moving. Okay. And then the second joint in this category is a friction contact. We already talked about these with particle statics. This would be drawn the same way that a frictionless contact would. So the problem just has to tell you that there's friction or tell you that there's not friction. And again, the way this works is, so if you try to translate body one into the surface, that is impossible. That degree of freedom is eliminated. Okay. And if you try to slide it perpendicular to that first axis, the friction keeps it from moving. Okay. So there's a full vector of unknown forces. What about repletion? If you rotate it, yeah, the friction doesn't have any effect on that. So again, a free body diagram of one looks like that, and we'll write it as the force on 1 by 2. And a free body diagram of 2 the unknown force is the force on 2 by 1, and Newton's third law says that's negative F12. Any questions about those? And now we're on to joint category 3. There's only one joint in this, it's a fixed joint, but this applies a force with an unknown direction and a couple. And this introduces 3 variables into Newton's laws. And the only joint in this category is a fixed joint. Or sometimes it's called a weld joint. You'll see it shown like this, where the thing just meets the object next to it. Or you'll sometimes see it shown like it's a sort of like a dovetail type joint. Those mean the same thing. So let's say that beam is body 1 and past the wall is body 2. A free body diagram of body 1. There's a force vector, and that's the force on 1 by 2, because all translation is eliminated. And then there's a couple that we'll call M12. That's the moment on 1 by 2. And then if you're doing the free body diagram of the other one, well, it can't rotate. Remember, what you're thinking of is the degrees of freedom that are eliminated. It can't move at all. Yeah, right. And that's a really easy common mistake to make. So just try to keep reminding yourself. We're not thinking about how it can move. We're thinking about how it can't move compared to something in outer space. Yep. Yes, but here, let me just draw this picture and then I'll talk about that. So, and then if you're doing the free body diagram of the wall, that would be the force on 2 by 1. So that's negative F12. And then this is the couple on 2 by 1, which is negative M12. Newton's third law has to work for couples too, because couples are really pairs of forces, you know, and it works for each one of the forces. Okay, so yeah, what's really happening is if you try to, so if you put a force on the end of this here, try to rip it out of the wall, you know, down. What's really happening is the wall is going to apply a force that way to the bottom of it, and that way to the top of it, and that's going to produce a moment that keeps it from rotating down. Okay, but since those things don't depend on the about point, and they don't add up to any net force because they're equal and opposite, we just treat it like it's a pure moment. It really is two forces, but mathematically it just works as a pure moment. So
those forces that create the moments aren't just contact forces?
No, that's right. That's a different thing. So the moments are what keep you from rotating it down, but there are also forces on there that keep it from sliding up or down the wall or sliding into or out of the wall. So that's F12. Yeah. Okay, so well, that introduces 3 variables by itself. So if you have a problem, you know, a body with a fixed joint, it can't have any other joints attached to it, or it's statically indeterminate. You can't solve it using statics. There are other ways around it, but you just can't use the ideas of statics by themselves. Okay.
Is this how you would represent a single object breaking?
Yeah, that's right. Yes, it is, exactly. Yep. Okay, let me do one quick free body diagram, and then we'll do the quiz and get out of here. So let's draw a free body diagram. Let's say that there's a pin joint over here and a roller here and a force applied there of 1,000 newtons. And let's say that the mass of this beam is 50 kilograms. Okay, well, draw an outline of the body. At the center of mass, there's a downward force of 50 kilograms times 9.81. So that's 490.5. And then there's the 1,000 Newton force there. At the pin joint at the left, what do we know about the loads that applies? Yep, that's a force with an unknown direction. So I'll write that here as, I don't know, F. And then what do we know about the loads applied by the roller? Yep, that's a normal force perpendicular to the surface of contact. So I'll write that as R. And now, is this something we could solve with statics? Yeah, because we have two unknowns for F, a third unknown for R. We have three equations, so that'll work out. Okay, let's do the quiz.